All right, so if we're going to talk about a roller coaster with an unknown mass. Okay. A roller coaster with an unknown mass. And you might have a roller coaster something like this. Make it a really simple one, no loops or anything. Kind of a boring roller coaster. Give ourselves a baseline. And we can define some basic heights. We can say, okay, this is height A. (10 meters). We can make this be height B. 5 meters. And this is going to be height C, 0 meters. Okay. And I want to put a coaster car at the beginning of this track. Now for argument's sake, just to make the calculations a little bit simpler so we can work through the idea relatively quickly, I want to say that this coaster starts off just at a velocity of 0 meters per second. And somehow it just gets nudged over the edge and it starts rolling. Now what I'd like to propose is that we could find velocity at position B. Well, let's find it at position C first. At position C. Let's make that part A. And people say, oh, you can't do that because you don't know its mass. You can't calculate EG or EK, and based on our earlier calculations, you need to know the mass to find EG and EK. But let's entertain this just for a moment anyways, okay? Let's say that we know that E total is equal to EG plus EK. And so at this position here and at this position here, the E total is going to be the same. So we could say E total at position A is equal to E total at position C. And we could start breaking down this formula into its component parts. We could talk about EGA plus EKA and EG at position C plus EG or EK at position C. And then we could start actually subbing in our values for EG and EK. We could say, all right, so this is mass times acceleration due to gravity times height A plus 1/2 mva squared equals mass times acceleration due to gravity times height at position C plus 1/2 mv at position C squared. Now this is a massless roller. Oh, it's not massless. It's an unknown mass for a roller coaster. Do I need to know the mass here? Absolutely not. You might think so. What could I do? What's a common term in each of these expressions? Mass. Sure. I could put mass out front of this binomial, acceleration due to gravity times height at position A plus 1/2 VA squared. And I could put mass out front, likewise, on the right-hand side of this equation of acceleration g times height at position C plus 1/2 VC squared. What can I do at this point to make the masses disappear? Yeah, divide by m. Divide both sides by m. And these m's cancel out. And so I could come up with a new formula. Acceleration due to gravity times height A plus 1/2 VA squared equals acceleration due to gravity times height C plus 1/2 VC squared. That's a really nice formula. And I could use that formula at position B as well. It's reusable. Now the thing is, when I calculate AG times height A, is that gravitational potential energy anymore? No, not really. There's no mass there. But that doesn't mean it's not helpful right now. It's just that if I do this calculation, this isn't actually EG anymore at position A. But it is still useful in finding VC if I wanted to. So actually, if we wanted to find VC at this point, in this particular position, this is a nice general formula for if I wanted to find V at position B as well. But at this particular position, I can make some simplifications. I can say, all right, at position C, the height is equal to 0. And at position A, the velocity was equal to 0. And so I can simplify this formula even further for this particular position. I could say that acceleration due to gravity times height at position A is equal to 1/2 VC squared. And if I want to get VC by itself, I multiply both sides by 2 and then square root both sides. So I get 2 times acceleration due to gravity times height A, all square rooted, is going to be equal to VC. And I can sub in some values. VC is equal to 2 times 9.81 meters per second squared times the height, which is 10 meters. Well, height at position A anyways is 10 meters. Units check out. Meters times meters is meters squared. Meters squared per second squared square rooted will give us units of meters per second, which is what we'd expect. What's the numerical value that goes along with, what's the coefficient that goes around along with those units? Has anybody got it? 2 times 9.81 times 10, all square rooted. What is it?
96, I'm just guessing.
Oh, you're just guessing. Okay. I'm relying on you guys. Come on, come on. Are you asking me to do the calculations and the writing? Come on, help me out here. See if you can do it.
14.
Is it 14? Okay, do we have a second person to pass that motion? You need to have your calculators out in physics class, people.
Wait,
It's 14.
14.
Okay.
Yeah.
Is it 14?
14.007.
Yeah. 7.
Okay. 14.0071 meters per second, and we can round that off to 3 sig figs of just 14.0 meters per second. So you see, we made use of the idea of gravitational potential energy, kinetic energy, and total energy, and setting them equal along the way here, but it's not necessarily essential for these 100% efficient systems, okay, to have the mass. You don't necessarily need the mass. Even though right here this is not gravitational potential energy, it's the mass eliminated from it, we're able to make that elimination because there's a mass in every term. Okay? Just a nice little thing to see.